Somewhere far above the fields and the rooftops and the slow-breathing rivers, the sky has always been quietly building something. Long before there were words for weather, long before anyone thought to count the seconds between a flash and a rumble, the air itself was already learning how to spark. Tonight, let your shoulders sink into whatever is holding you, let your eyelids grow heavy, and let this slow, drifting voice carry you through the gentle, humming science of lightning, one soft fact folding into the next, like clouds folding into each other before a summer storm. High in a thunderstorm, ice crystals and hail pellets are constantly colliding, tumbling over one another in the cold upper reaches of the cloud, and every collision leaves behind the faintest whisper of electric charge. Smaller ice crystals drift upward on rising air, carrying a gentle positive charge with them, while heavier hail and slushy ice, called graupel, sink toward the base of the cloud, carrying a negative charge along for the ride. In this way, without anyone directing it, the storm slowly separates itself into layers, positive above, negative below, the way warm milk might separate from honey if you let a jar sit undisturbed on a quiet counter overnight. This separation of charge is the real beginning of every flash of lightning you have ever seen, and it happens so quietly, so far above our heads, that we never notice it building. The cloud becomes, in effect, an enormous battery, cold and slow and patient, storing its energy the way a held breath stores air, waiting for the moment it will finally let go. Down below, on the ground beneath the storm, something answers. The negative charge pooling at the base of the cloud pushes away the negative charges in the earth below it, leaving the ground itself carrying a soft positive charge, reaching upward, invisible and eager, like grass leaning toward sunlight. Trees, hilltops, church steeples, the corners of tall buildings, even a person standing alone in an open field, all of them can raise this positive charge a little higher, straining upward through the humid air, though none of it can be seen by the eye. Between the cloud and the ground, the air itself is normally an excellent insulator, keeping charge apart the way a thick blanket keeps warmth in. But as the charge builds, the electric field grows so strong that the air can no longer hold the line. And so a thin, invisible thread of ionized air, called a stepped leader, begins to grope downward from the cloud in short, jagged, hesitant steps, each one only about 50 meters long, pausing for a few millionths of a second between steps, as if feeling its way through the dark, the way your own hand might feel along a wall in an unfamiliar room at night. This stepped leader branches as it falls, splitting into many faint fingers reaching for the ground at once, most of them invisible to anyone below, all of them searching. And rising up to meet it, from treetops and rooftops and the shoulders of hills, come faint streamers of positive charge, reaching upward the way a sleepy hand might reach up out of a blanket toward a familiar voice. When one of these downward branches finally meets one of these upward streamers, usually somewhere just above the ground, a complete channel is formed, a single unbroken thread connecting the cloud to the earth. And then, in a moment far too fast for our eyes or minds to properly register, a surge of current rushes upward along that thread, from the ground into the cloud, in what is called the return stroke. And this return stroke is the blinding, brilliant flash that we actually see and call lightning. It is a strange and gentle irony that the visible flash of lightning, the one that seems to fall from sky to earth, is in fact traveling in reverse, rushing upward from the ground into the clouds, chasing the very channel that reached down to find it. The return stroke moves upward at roughly 1/3 the speed of light, which is faster than almost anything else you will ever witness with your own eyes. And yet the whole event, from the first faint stepped leader to the final fading glow, usually lasts less than half a second, gone almost before your mind has finished forming the thought lightning. Within that half a second, the channel of air the lightning travels through is heated to something close to 30,000 Kelvin, a temperature hotter than the surface of the sun, hot enough to instantly boil the water inside the wood of a struck tree, and hot enough to fuse grains of sand into strange hollow tubes of natural glass beneath the ground. The air along the channel expands so violently, so suddenly, that it sends a shockwave rippling outward in every direction. And that shockwave, as it slows and spreads, becomes the low, rolling rumble that we call thunder. Because light travels so much faster than sound, we always see the flash before we hear its voice. And in that small, quiet gap between seeing and hearing lies one of the oldest, gentlest tricks anyone ever taught a child on a porch during a summer storm: counting slowly after the flash. One full count for each mile the sound still has to travel, about 5 seconds for every mile, or 3 seconds for every kilometer. A hush of counting that turns a storm into something almost like a lullaby. Something you can measure, something you can hold. A single bolt of lightning, despite its blinding brightness, actually carries only a modest amount of energy compared to what our modern world consumes, though the way that energy arrives all at once, compressed into a fraction of a second, makes it feel enormous, makes it feel like the whole sky has decided to speak a single, thunderous word and then fall silent again. Across the entire planet, at any given moment, there are roughly 2,000 thunderstorms quietly rumbling somewhere on Earth's surface. And together, day and night, without pause, they produce something like 40 to 50 flashes of lightning every single second, which adds up to somewhere around 8 million lightning flashes crossing the sky of our planet every single day. A soft, continuous electrical hum wrapped gently around the whole spinning Earth. Most of it far out over oceans and jungles and mountains where no one is awake to notice. Much of that lightning never even touches the ground at all. The most common kind of lightning, by a wide margin, occurs entirely inside a single cloud, or leaps between two neighboring clouds, lighting the underside of the storm from within like a lantern glowing softly through canvas, a flicker you might catch from your window without ever hearing its thunder at all, because sound, unlike light, fades and bends and gets swallowed by distance far more easily. Cloud-to-ground lightning, the kind most of us picture first, the jagged bright fork reaching down to touch a hillside or a lone tree, makes up only a small fraction of all the lightning that happens, perhaps one flash in every 4 or 5. And of that smaller fraction, the great majority carries a negative charge downward, while a rarer, often far more powerful kind carries a positive charge instead, striking sometimes many miles away from the storm that produced it. Out of a clear patch of sky where no rain is falling at all, a bolt that seems, to anyone standing there, to have come from nowhere. This is why old warnings about storms are often gentler and wiser than they sound at first. The idea that a storm can reach out and touch you even after it seems to have already passed, even when the sky above your own head looks calm and clear, because the charge overhead does not always announce itself with rain. Lightning has been part of every culture that ever looked up at a stormy sky and wondered what force could possibly move so fast and strike so suddenly. Ancient people watched the same forked light we watch today, and across nearly every corner of the world, they decided, independently, that only a god could throw something so bright and so final. In ancient Greece, it was Zeus who held the thunderbolt as his signature weapon, a jagged spear of fire he could hurl down from Mount Olympus whenever mortals displeased him. In Norse mythology, it was Thor, riding his chariot across the sky, whose hammer Mjolnir struck sparks that lit the clouds each time it met its mark. In many West African traditions, it was Shango, fierce and proud, who commanded both fire and thunder as twin expressions of the same restless power. In Hindu tradition, it was Indra, wielding the Vajra, a weapon said to be forged from the bones and fury of a sage, capable of splitting mountains as easily as clouds. Halfway around the world, in the oral traditions of many indigenous nations of North America, it was the thunderbird, a creature of impossible wingspan, whose beating wings stirred thunder itself, and whose glowing eyes released lightning with every blink, said to nest on the highest, most storm-wrapped peaks, far above where any hunter could climb. It is a strangely comforting thought. if you let it settle over you slowly, that every person who ever lay awake listening to a storm, in every century and on every continent, heard roughly the same low rumble you hear tonight, and reached, in their own way, in their own language, for some story large enough to explain it. It would take until the middle of the 18th century for anyone to test, with real evidence rather than mythology, the quiet suspicion that lightning was not the anger of a god but simply electricity, the very same mysterious force that scientists of the time were already coaxing out of glass rods and static charge jars in their laboratories. Benjamin Franklin in Philadelphia proposed a now famous experiment, flying a kite into a storm with a metal key tied near the string, reasoning that if lightning truly was electricity, the storm's charge would travel down the wet string to the key, and there, carefully from a safe distance, he could draw a spark from it. Franklin performed some version of this experiment in 1752 and lived to describe what he felt, though not everyone who repeated it in the years that followed was so fortunate, and history quietly remembers at least one European scientist who was killed attempting the very same test not long afterward. A soft and sobering reminder tucked inside this often triumphant story. Out of that same insight, that lightning was electricity and could therefore be guided, Franklin devised the lightning rod, a simple pointed metal spike mounted above a building and connected by a thick wire down into the ground, offering the electricity an easier, safer path to follow than through the timber and stone and people below. It remains, more than 2.5 centuries later, essentially unchanged in its basic principle, quietly doing its job on rooftops around the world during storms just like the one that might be humming somewhere outside your own window tonight. Unnoticed, unglamorous, simply waiting. Let your breathing slow now in time with the story in and out, the way a storm itself seems to breathe, building slowly, releasing suddenly, and settling again into quiet. There's so much more of this soft, electric world still to drift through together. Cloud shapes and glowing spires and strange lights above the storm tops that scientists only fully confirmed within living memory. And we will keep unfolding them slowly, one gentle fact at a time, for as long as it takes, across as many quiet turns as this story needs, until the whole 100 has been told and the whole 200,000 words have settled like fine, quiet rain into place. For now, simply rest here, in the space between the flash and the thunder, in that soft 5-second hush where the sky has already spoken and the ground is still waiting to answer, and let that waiting be enough. Let's drift a little further into the storm now, past the part we can see and into the part that mostly hides itself from us. Most lightning, as the story already whispered, never leaves its cloud at all, and this quiet, hidden majority is called intracloud lightning, a flicker of current that travels between the positive region near the top of a storm and the negative region lower down, all within the same towering column of vapor and ice. Illuminating the cloud from the inside the way, a lantern glows through the fabric of a tent, softening the whole night sky into a slow, pulsing amber, without ever once touching the ground below. When the charge instead leaps sideways, from one cloud to a neighboring cloud entirely, it is called cloud-to-cloud lightning, and on certain nights, when a whole line of storms marches across the horizon together, this kind of lightning can look like a conversation, one cloud flickering, and moments later, another cloud answering back and forth, the way distant lighthouses along a coastline seem to blink to each other across dark water, each one simply doing its own quiet work, though it feels, to anyone watching from far below, like a kind of speech. Higher still, above the very top of the tallest thunderstorms, in the thin, cold air, where the atmosphere begins to fade into the edge of space, there are lights that scientists only confirmed with certainty in the final years of the 20th century, even though pilots had described them in hushed, uncertain reports for decades before anyone believed them. These are called sprites, and they appear as faint reddish, jellyfish-shaped flickers, blooming silently for only a few thousandths of a second, far too fast and far too high for most people to ever notice from the ground. Sprites are triggered by the largest, most powerful strokes of positive lightning far below them, an electrical echo thrown upward into the edge of the ionosphere, a kind of answer sent from the storm to the almost space above it. Even higher and even briefer than sprites are the elves, an affectionate name built from a much longer scientific phrase, and they appear as fast, expanding rings of dim red light, spreading outward across the lower ionosphere in less time than it takes a hummingbird's wing to complete a single beat. So fast that early researchers needed specially built high-speed cameras just to prove the elves were really there at all, glowing and gone before the human eye could ever hope to catch them unaided. And rising up from the very tops of certain especially powerful storms, mostly seen from aircraft or from mountaintop observatories on clear nights, are blue jets, narrow cones of blue-violet light that shoot upward from the cloud top into the stratosphere, climbing for a fraction of a second before fatting, named simply for the color they wear and the quickness with which they leave, a shy, fleeting cousin of the more familiar lightning below. There is another kind of lightning, rarer and stranger still, that has unsettled and fascinated people for centuries without ever being fully explained even by modern science, called ball lightning. Unlike ordinary lightning's instant flash, witnesses across many different countries and many different centuries have described a glowing sphere, sometimes the size of an orange, sometimes as large as a beach ball, drifting slowly through the air, sometimes passing through open windows, hovering near ceilings or rolling gently along the ground, lasting anywhere from a few seconds to what some witnesses insist was closer to a full minute, before vanishing quietly or occasionally with a small pop, leaving behind nothing but a faint smell like burnt metal and a room full of people who cannot quite agree on what they just saw. A gentler, far more common glow, one that sailors have long trusted as a kind of quiet weather omen, is called St. Elmo's fire, named for the patron saint of sailors. It is not lightning itself, but rather a related electrical phenomenon, a soft, hissing, bluish or violet glow that appears at the tips of pointed objects, ship masts, aircraft wingtips, church spires, even the raised horns of cattle in a field, whenever the surrounding air becomes so charged that it begins to glow on its own, without ever forming a full connecting spark. A quiet fizz of light that many old sailors took as a sign the worst of a storm's temper had already passed, or was still building just out of sight. Some of the fiercest lightning on the entire planet has nothing to do with rain clouds at all, but rises instead from the shuddering throat of an active volcano. As ash, rock fragments and ice particles are hurled violently upward and collide within the churning eruption column, they build a static charge in almost exactly the same way as colliding ice does in an ordinary thunderstorm, and the result, called volcanic lightning, can flicker in bright jagged forks through billowing dark ash clouds, a phenomenon so visually strange, so ancient and reptilian in feeling, that photographs of it are often mistaken by people seeing them for the first time as something almost unearthly. Another kind of lightning carries its own quiet danger precisely because it announces so little. Dry lightning occurs when a thunderstorm produces lightning, but so little rain reaches the ground, evaporating instead in the hot, dry air far above, that the strike lands on parched grass, dry brush, or drought-stressed forest with almost nothing to extinguish the resulting spark. And dry lightning is responsible for igniting a significant share of the largest wildfires in dry regions of the world, a storm that seems, from a distance, to be giving nothing at all, and yet leaves fire behind it regardless. Because thunder can only be heard for a limited distance, often no more than about 10 miles under good conditions, and because the most dangerous part of a storm can arrive well before the first drop of rain, and linger well after the rain has stopped, meteorologists and safety experts have long recommended what is sometimes called the 30-30 rule, seeking shelter if the gap between seeing a flash and hearing its thunder is 30 seconds or less, and waiting a full 30 minutes after the very last rumble before venturing back outside. A small, Patient discipline that has quietly saved a great many lives over the years, precisely because it does not trust the sky's silence too quickly. Somewhere in the drowsy quiet between one fact and the next, let your thoughts loosen a little further, the way a knot loosens once you finally stop pulling at it. There is no need to hold onto any of this tightly. Let the sprites and the jets and the slow blue glow at a ship's mast simply drift past you like clouds themselves, each one passing overhead, each one leaving only the faintest shadow, while the story keeps unspooling gently, fact after fact, breath after breath, for as long as you need it to. There is a place on Earth where this whole slow story of charge and cloud and release repeats itself more often and more intensely than anywhere else on the planet. A stretch of warm water and marshland in western Venezuela where the Catatumbo River empties into Lake Maracaibo. There, warm, moist air sweeping off the lake collides night after night with cool air pouring down from the surrounding mountains. And the result is a storm system so faithful, so relentless, that lightning flickers above that lake on more nights of the year than almost anywhere else ever recorded, sometimes flashing for 9 or 10 hours in a single night, over and over. A natural lighthouse so steady and so bright that sailors navigating the Caribbean centuries ago are said to have used its distant glow to help find their bearings in the dark, long before anyone had given the phenomenon a name in any scientific journal. Most lightning, ordinary and unremarkable as it is in the grand scheme of the storm that made it, carries only a modest amount of true destructive force, but every so often, a storm produces something enormously more powerful, a stroke so intense that researchers had to invent a new word for it entirely, calling it a superbolt. A superbolt can release something like 100 times or even 1,000 times more energy than a typical flash, and satellite instruments watching Earth from orbit have found that these rare giants tend to cluster in certain places more than others, especially over open stretches of ocean during the colder months, as though the sea itself, wide and dark and endless, occasionally needs to answer the sky with something equally large. Most cloud-to-ground lightning begins high in the storm and reaches downward toward the Earth, but very tall structures, extremely tall towers, skyscrapers, and mountaintop antennas can sometimes flip that whole quiet process on its head, initiating a stepped leader that climbs upward from the structure itself into the base of the storm above, in what is called upward lightning. This tends to happen most often from structures taller than a few hundred meters, and it means that certain very tall buildings do not simply wait passively to be struck, but occasionally, in their own way, reach up first, extending a slender questioning finger of charge into the clouds before the answer comes flooding back down. The Empire State Building, rising for decades as one of the tallest structures on Earth, has been struck by lightning so many times across its long life, sometimes several times within a single storm, that early engineers studying it were able to use its steel frame almost like a natural laboratory for understanding how enormous structures interact with a storm's electric field, each strike sliding harmlessly down through its grounded steel skeleton into the earth below. The building shrugging off in half a second, what would destroy almost anything built without that same careful, deliberate path to ground. While negative cloud-to-ground lightning is the far more common variety, positive lightning, though rarer, tends to be considerably more dangerous, carrying higher peak currents, lasting longer, and capable of traveling many miles horizontally away from the storm that generated it before finally reaching down to the ground, which is part of why weather safety guidance has slowly shifted over the decades, away from the old assumption that clear skies overhead mean real safety, and toward a gentler, more cautious rule that the threat of a storm lingers long after its edge has visibly passed. The odds of any one person being struck by lightning in a given year are extremely small, something like 1 in over 1 million in many countries, and the lifetime odds, stretched out across an average human lifespan, land somewhere closer to 1 in 15,000, numbers small enough that being struck remains a genuine rarity, and yet large enough, across the full population of a restless, outdoor-loving species. That meteorologists still record several hundred lightning-related deaths worldwide each year, most of them among people caught in open fields, on boats, or beneath isolated trees, precisely the places the leader current finds easiest to reach. A person who survives a lightning strike, and the great majority of people struck by lightning do survive it, often carries strange and lingering marks of the encounter, faint branching red patterns on the skin called Lichtenberg figures, named for the German physicist who first studied similar branching patterns in dust on charged surfaces, temporary marks that trace, almost like a photograph, the fern-like path the current took across the surface of the body before fatting. Usually within a day or two, without leaving any permanent scar behind at all, a strange, brief signature written and erased by the same storm. Deep in the desert or along certain beaches, long after a storm has passed and the lightning itself is only a memory, it is sometimes possible to dig up a strange, brittle, glassy tube shaped roughly like a lightning bolt frozen in place, called a fulgurite. These form in an instant, when the extreme heat of a ground strike fuses the silica in sand or soil into natural glass along the exact path the current traveled underground, leaving behind a hollow, root-like structure that can sit buried and perfectly preserved for years. A fossil in its own strange way, not of any living thing, but of a single half-second of electricity, held forever in the shape it happened to take. Lightning does something else too, quiet and unglamorous, that has mattered enormously to life on this planet for a very long time. The intense heat of a lightning channel is powerful enough to briefly break apart the extremely stable nitrogen molecules that make up most of our atmosphere, allowing that nitrogen to combine with oxygen and eventually fall to Earth in rain as compounds that plants can actually absorb through their roots, a process called nitrogen fixation. Long before humans learned to manufacture nitrogen fertilizer in factories, storms were already doing this work quietly, season after season, feeding the very soil that feeds nearly everything that grows, an invisible act of gardening performed by the sky itself. Out over open water, sailors and researchers have long noticed that certain regions seem to draw storms and their lightning again and again. And modern satellite mapping has confirmed what those old sailors suspected by instinct, that lightning activity is heavily concentrated over land, especially over certain tropical regions of Africa, South America, and Southeast Asia, where warm, moist air rises fastest and most often, while the open ocean, despite covering most of the planet's surface, produces comparatively less lightning per square mile, quieter out there most nights than the humming, restless land. Let the weight of your own body sink a little further now into whatever is beneath you, mattress or cushion, or simply the crook of your own folded arms, because this story is not in any hurry at all. There will be time enough, across many more slow turns like this one, to drift up past the clouds entirely, out past the edge of our own atmosphere, to where other worlds spinning through the same dark solar system have their own storms, their own lightning, some of it far stranger and far more violent than anything our gentle blue planet has ever produced. Drift now slowly past the moon, past the last thin traces of our own atmosphere, out toward the giant planets that circle the sun far beyond us, because it turns out that Earth is not the only world with weather loud enough to spark. Jupiter, the largest planet in the solar system, wrapped in swirling bands of ammonia cloud, produces lightning of its own. First suspected when the Voyager spacecraft passed by in the late 1970s and recorded strange radio bursts, later confirmed by later missions that captured actual images of bright flashes glowing on the planet's night side, lightning that tends to cluster near Jupiter's poles, born from water clouds deep within its thick, turbulent atmosphere, in storms so vast that a single one could swallow our entire planet without noticing it had done so. Saturn too has its storms, and in the early 2010s, the Cassini spacecraft, quietly orbiting the ring planet for over a decade, detected an enormous storm nicknamed the Great White Spot, wrapping nearly all the way around Saturn's northern hemisphere, crackling with lightning so intense that its radio emissions were, for a time, the loudest electrical storm noise ever recorded anywhere in the solar system. A storm that raged for months, far longer than any thunderstorm ever seen on Earth, before it finally, slowly quieted. Venus, closer to home and wrapped in thick, crushing clouds of sulfuric acid, has left scientists in a long and gentle disagreement about whether it truly has lightning at all. Some spacecraft instruments have picked up radio signals that resemble the signature of lightning strokes, while others have found no clear visual flashes to match. And so Venusian lightning remains one of those soft, unresolved mysteries the solar system still keeps to itself, a question mark hanging in that thick yellow sky, waiting for some future mission to finally settle the matter one way or the other. And far out at the edges of the solar system, even the cold blue giants Uranus and Neptune, wrapped in frigid atmospheres of hydrogen, helium, and methane, are believed, based on faint radio signatures caught by passing spacecraft, to generate their own lightning deep within their swirling cloud decks, storms so distant and so dim that we may never actually see one flash with our own instruments, only hear its faint electrical whisper crossing billions of miles of empty space to reach us. Back on our own quieter planet, storms hide another secret that scientists only fully uncovered within the last few decades, something that would have sounded like pure science fiction to Benjamin Franklin flying his kite. Some of the most powerful thunderstorms produce brief, invisible bursts of gamma radiation, the same high-energy light associated with nuclear reactions and distant collapsing stars, in events called terrestrial gamma ray flashes. These bursts last only a few thousandths of a second, produced when the intense electric fields inside a storm accelerate electrons to extraordinary speeds, and they were first noticed, almost by accident, by satellites built to watch for gamma rays arriving from deep space, instruments that kept detecting flashes seemingly coming from Earth itself, from directly beneath them, from the quiet tops of thunderstorms drifting along below. Researchers eventually grew curious enough about lightning's exact behavior that they stopped waiting for storms to strike on their own, and instead began triggering lightning deliberately, launching small rockets trailing a thin grounded wire up into the base of a charged thunderstorm, giving the cloud's built-up charge an easy, predictable path to follow down to instruments waiting on the ground. This technique, called rocket-triggered lightning, has let scientists study, in careful, repeatable detail, the exact currents, timings, and behaviors of a stroke that would otherwise strike wherever and whenever it pleased, transforming lightning from something merely watched into something that could, in a small and controlled way, be summoned. Animals living through a storm experience it differently than we do, and not always more safely. Cattle and other livestock standing in open pasture are considered especially vulnerable, not usually because lightning strikes them directly, but because a strike landing anywhere nearby can send current spreading outward through the wet ground in a phenomenon called ground current. And a large four-legged animal standing with its front and back legs far apart creates a bigger voltage difference across its own body than a person standing with 2 feet close together, which is part of the quiet reasoning behind old advice to keep your feet together and crouch low, rather than lie flat, if ever caught outdoors with nowhere safer to go. Tall, solitary trees standing alone in an open field are struck far more often than trees growing together in a forest, not because lightning prefers solitude exactly, but because the tallest, most isolated point in any given stretch of land offers the easiest, shortest path for the storm's downward-reaching leader to finally meet the upward-reaching streamer from the ground. And this same simple principle, that height and isolation attract a strike far more than character or fate ever could, is the quiet logic behind almost every piece of lightning safety advice that has ever been written down. Even the ocean is not entirely calm during a storm passing overhead. Sailors have long known to avoid being the tallest point on the water, and modern data confirms that lightning strikes on boats, particularly sailboats with tall metal masts, are common enough that many vessels are now built with dedicated grounding systems, bonding the mast down through the hull into the water itself, giving any strike a clear path to dissipate harmlessly into the vast conductive sea below, rather than through the wood, the wiring, or the people standing on deck. Let your eyes rest fully closed now if they have not already, because none of this needs to be pictured sharply, none of it needs to be remembered in detail. Let Jupiter's glowing poles and Saturn's long, murmuring storm and the small bright rocket trailing its wire up into a waiting cloud all blur softly together at the edges, the way distant things always blur just before sleep finally arrives. And rest easy knowing there is still so much more of this slow story left to unfold, patiently, across turn after turn, for as long as this night needs it to continue. There are certain places on the surface of our own planet that seem to draw storms the way a low valley draws fog, quietly, faithfully, year after year, and scientists tracking lightning from satellites have slowly built up a map of these restless hotspots. A small village called Kifuka, nestled in the mountains of the Democratic Republic of the Congo, has long been cited as one of the most lightning-dense places on Earth. Its high elevation and warm, moist convection combining night after night into storms that flicker with a frequency few other places can match. Lake Maracaibo, with its faithful Catatumbo glow, sits not far behind it, and across the ocean, a wide stretch of central Florida, sometimes nicknamed Lightning Alley, sees more strikes each year than almost anywhere else in North America. The warm Gulf air and the warm Atlantic air meeting over that narrow peninsula almost every summer afternoon, brewing storms with such quiet regularity that longtime residents learn, the way people everywhere eventually learn their own local sky. Exactly which hour of the afternoon to expect the first low rumble. The color of a lightning bolt, though it flashes and fades too quickly for most eyes to study closely, actually carries a faint signature of the very air it passed through. A bolt that appears mostly white or pale blue is usually traveling through relatively dry, clean air. A flash tinted with a soft reddish or pink hue often suggests the presence of rain droplets scattering the light along the channel. And lightning that briefly glows with a yellowish or orange cast can sometimes indicate dust or sand particles suspended in the atmosphere it passed through, so that a storm's lightning, in its own brief and wordless way, is quietly reporting back on the condition of the very sky that produced it, a message written and erased within the same half-second. Long before satellites could watch storms from above, and long before rockets could deliberately summon lightning down to a waiting sensor, curious scientists tried to recreate lightning's basic mechanism in the laboratory using far gentler tools. Large static generators, towering globes and belts of rubber and metal capable of building up enormous but comparatively tame voltages, allowed researchers to produce miniature sparks under controlled conditions, studying, in careful, repeatable miniature, the same basic behavior of charge separation and sudden discharge that plays out on a vastly larger scale inside every thunderstorm, a small tabletop echo of the sky's own oldest trick. Modern meteorologists no longer need to wait for a storm to march directly overhead before knowing it is coming. Satellites parked in high geostationary orbit now carry instruments built specifically to watch for the telltale flicker of lightning across enormous stretches of the Earth's surface continuously, day and night, spotting storms forming over remote oceans or unpopulated mountain ranges long before any ground-based radar or human observer would notice them at all, feeding that information quietly back down to forecasters, who can then offer warnings to towns and airports and ships that might otherwise have had no warning at all beyond the sky itself darkening on the horizon. Before any of these tools existed, before radar, before satellites, before the very word electricity had settled into common use, storm chasing of a very different, very patient kind had already been happening for centuries in the form of simple weather lore, passed down mostly by word of mouth from one generation to the next. Sailors watching the color of the sky at dusk, farmers watching which way the leaves of certain trees turned before a storm, shepherds watching how their flocks grew restless hours before the first flash appeared. All of it a kind of folk meteorology built entirely from patient observation. Some of it later proven scientifically accurate, some of it simply comforting, and nearly all of it aimed at the same quiet goal that still occupies meteorologists today: understanding just a little further in advance when the sky is about to speak. Let your thoughts settle now on nothing more demanding than the shape of a distant, half-remembered storm, the kind you might have watched as a child from a porch or a car window, more curious than afraid, counting slowly after each flash the way this story already described: 1, 2, 3, 4, 5, learning without quite realizing it that the sky, however loud and sudden it seemed, was also something that could be measured, something with a rhythm, something that always, eventually passed. A single thunderstorm cloud, from its flat dark base to its towering, anvil-shaped top, can sometimes stretch upward for 10 miles or more, taller than any mountain on Earth, and within that great vertical column, air is rising and falling at the same time in different places, warm moist air surging upward through the updraft at speeds that can exceed 60 miles an hour, while cold rain and hail plunge back downward through the downdraft only a short distance away. And it is this constant churning, this endless vertical wrestling match between rising and falling air, that keeps the ice crystals and hail colliding long enough to build the charge that eventually becomes lightning. A storm's entire electrical life depending, in the end, on nothing more complicated than air refusing to sit still. The flat, spreading top of a mature thunderstorm, the shape most people picture instantly when they imagine a serious storm rolling in, is called an anvil, so named because it resembles the flat striking surface of a blacksmith's anvil, formed when the rising column of air finally reaches a layer of the atmosphere it cannot push through any further, called the tropopause, and spreads sideways instead, sometimes for many miles in every direction, casting the storm's shadow far ahead of the storm itself. So that on certain afternoons you might notice the sky darkening and the light turning strange and green long before any thunder has actually reached your ears. That strange greenish tint some storms take on, particularly in the hour before a very severe storm arrives, has long been treated by experienced weather watchers as a quiet, informal warning sign, thought to result from sunlight filtering through an unusually thick, hail-laden cloud at a particular angle, though meteorologists are careful to note that the green sky itself does not directly cause severe weather, only tends to accompany the kind of towering, hail-heavy storm that often does. A color that folk memory long ago learned to treat with a little extra caution. Power grids and electrical infrastructure remain, even in an age of satellites and gamma-ray detectors, deeply vulnerable to something as old and simple as a direct lightning strike. And utility engineers spend enormous effort designing transmission towers, substations, and grounding systems, specifically to give a stray strike somewhere safe to go before it can surge into homes and damage sensitive electronics. Which is part of the quiet reasoning behind the old advice to unplug delicate devices during a severe storm, not because the storm is likely to strike your own home directly, but because a strike landing on a power line miles away can still send a spike of current traveling down the wire and into whatever happens to be plugged in at the far end. Airplanes, remarkably, are struck by lightning far more often than most passengers ever realize. Commercial aircraft flying through or near storms are estimated to be struck on average about once every 1,000 or 2,000 flight hours, and yet this rarely causes any real danger, because an aircraft's metal skin, or in modern planes, a carefully engineered conductive mesh woven into composite materials, acts much like a hollow metal box, letting the current flow harmlessly around the outside of the fuselage and back out into the air rather than through the cabin or the people seated inside. a principle borrowed from the same basic physics that keeps a person safe inside a grounded metal car during a storm, cushioned not by the tires as old folklore often claims, but by the conductive metal shell surrounding them. Lightning safety guidance has slowly grown gentler and more precise over the decades as researchers learned more about exactly how people are struck, moving away from older, less reliable advice and toward a small handful of well-tested principles. Seek a fully enclosed building rather than an open shelter. Avoid being the tallest object in an open area. Stay away from water, metal fences, and isolated trees. And remember that a storm's danger lingers well beyond the moment the rain finally stops falling. Small, quiet rules built from decades of careful, sometimes sorrowful observation, offered now simply as part of this story rather than as any urgent instruction, since nothing tonight requires your alertness at all, only your slow, steady breathing. Let your whole body soften a little further into stillness now, shoulders, jaw. The space between your eyebrows you may not have noticed was tense at all until this very moment, because there is truly nothing left to watch for here. No flash to count, no thunder to measure, only this long, unhurried voice, moving at its own unhurried pace through fact after fact after fact, patient as a storm that has already spent its lightning and is simply, quietly, raining itself out. In the late 1800s and into the early 1900s, as the age of electricity truly began, a handful of inventors and researchers grew fascinated not just with lightning as a natural event, but with the idea of generating something similar, something controlled in their own workshops. Nikola Tesla, working in his laboratory in Colorado Springs, built enormous coils capable of producing artificial lightning bolts many feet long, filling his workshop with a crackling violet light and a smell of ozone, chasing, in his own singular way, a deeper understanding of how electricity might one day be sent through the air itself rather than through wires, and though many of his grandest ambitions were never realized. His experiments left behind photographs of man-made lightning that still startle people who see them for the first time, bright jagged branches captured indoors, tamed just long enough to be measured. Charge, once it exists, is a patient thing, and even calm, cloudless air carries a faint natural electric field at all times, quietly present between the ionosphere far above and the ground far below, so gentle under ordinary conditions that no one would ever notice it without sensitive instruments. And it is only when a storm concentrates and intensifies that field by many, many times over that lightning finally becomes possible, meaning that in a very real sense, the electricity behind every bolt of lightning was always faintly present in the air around us, simply waiting for a storm patient enough to gather it all into one place. Ball lightning, that rare glowing sphere described earlier drifting through rooms and open windows, has resisted every attempt to fully explain it in a laboratory, though researchers have proposed a number of gentle, competing theories over the years, some suggesting it might be a slowly cooling ball of ionized gas called plasma, others proposing it could involve tiny burning particles of silicon vaporized from soil by a nearby strike, and still others wondering whether some reported sightings might simply be a trick of a dazzled, adrenaline-charged mind in the seconds after a nearby flash. And because true ball lightning is so rare and so unpredictable, arriving with no warning and vanishing just as quickly, it remains one of the few atmospheric phenomena that modern science can describe in careful second-hand detail, while still not being entirely sure it has ever captured one cleanly on film. Certain regions of the world experience so little lightning that its rare appearance becomes a kind of local event in itself, while other regions, mostly clustered in the warm, humid tropics, see so much lightning that a single county might record more strikes in a single summer than an entire northern nation sees in a decade. And this uneven scattering of lightning across the globe follows, quite faithfully, the uneven scattering of warmth and moisture across the globe, because lightning, in the end, is simply one of the ways a restless atmosphere balances its own inequalities, moving warm air upward, cold air downward, and charge from cloud to ground, all in the same unhurried effort to smooth itself back toward balance. Even snow, usually associated with quiet, hushed, lightless winter nights, occasionally produces its own rare cousin of ordinary lightning, called thundersnow, when a sufficiently unstable winter storm manages to generate the same kind of vigorous updraft that powers a summer thunderstorm, only with snow falling instead of rain. Thundersnow is considered unusual enough that many longtime residents of snowy regions will recall, quite specifically, the handful of times they ever witnessed it. A bright flash briefly illuminating a whole hushed, snow-covered street, followed by a low, muffled rumble that seems, wrapped in all that snow, softer and stranger than ordinary summer thunder ever sounds. Rest a little further now, if you can, into the hush of that very same imagined snowfall, thick and quiet and endless, each flake drifting down slower than the last, because there is nothing urgent left in this story at all, only more of the same slow unfolding, more soft evidence of a sky that has always, in every season and in every corner of the world, found some quiet way to speak. Seasons shape lightning almost as strongly as geography does, and across much of the temperate world, the great majority of thunderstorms cluster into the warmer months, when the sun has enough time and enough strength to heat the ground thoroughly, sending warm, moist air rising in strong, towering columns each afternoon, which is why so many childhood memories of summer, in so many different countries, seem to include at least one distant, rumbling storm arriving in the late afternoon heat. Almost as reliably as the heat itself, while winter's colder, more stable air, though occasionally still capable of that rare hushed thundersnow already mentioned, mostly keeps its own quiet counsel until the warm months return. Forests, though they are struck by lightning constantly, are not simply passive victims of the storms that pass over them, but have, in many ecosystems, come to depend on fire, and therefore in a roundabout way on lightning, as an essential part of their long, slow renewal. Certain pine forests, for instance, produce cones sealed shut with a resin that only melts and releases its seeds after exposure to real heat, meaning those trees have quietly built their entire reproductive strategy around the eventual arrival of a lightning-sparked fire, treating what looks to us like disaster as simply another, slower kind of season, one that clears old growth away to make room for the next. Modern satellites dedicated to lightning research have grown remarkably sensitive since the earliest instruments, and one such instrument, riding aboard a geostationary, whether satellite parked in a fixed position above the Americas, watches for the telltale optical flash of lightning continuously across an enormous stretch of the hemisphere, day and night, cataloging flashes with such precision that forecasters can now watch a storm's lightning activity intensify in something close to real time. Often minutes before that same storm produces damaging wind or hail at the ground, turning lightning itself into an early, quiet messenger of trouble still to come, rather than merely a symptom of trouble already arrived. Lightning has left its mark on human art and storytelling far beyond the old thunder gods already mentioned, appearing in paintings meant to capture the sublime, overwhelming scale of nature, in photographs long exposed across a whole dark sky to catch a single fork of light that lasted less than a second, and in countless songs and poems that reach for the same handful of comparisons again and again. A whip, a crack, a vein of silver, a sudden question the sky asks and immediately regrets. Each generation finding its own small new way to describe the exact same old flash our ancestors watched from caves and huts and rooftops long before any of them had a word for volts or amperes or ionization. The leader that gropes downward from a storm, described earlier in its halting, stepwise fashion, does not travel in a straight line. And this is part of why real lightning looks so different from the smooth, curved bolts often drawn in cartoons, branching instead into dozens of jagged offshoots as it descends, most of which fade into nothing the instant the main channel successfully connects to the ground, leaving only the single dominant path illuminated in the brief return stroke. Though careful high-speed photography can sometimes catch the ghostly outlines of those abandoned branches still faintly glowing in the final image, like sentences a sky started and decided, at the very last moment, not to finish. Let the shape of that word, unfinished, settle over you gently now, because there is nothing here that needs finishing quickly either, no branch that must be followed to its end, no thought that needs completing before your eyes are allowed to close. The story will simply keep branching softly onward, fact folding into fact, for as long as this night and the many nights after it continue to need it. A thundercloud does not build its charge evenly throughout its whole towering height, but instead tends to organize itself into a rough tripole, a small pocket of positive charge near the very base of the cloud, a much larger region of negative charge sitting just above it, and the great broad positive region spreading across the upper reaches near the anvil. 3 quiet layers stacked one atop another like a cake, no one baked on purpose. And it is the interaction and imbalance between these 3 layers, shifting and jostling as the storm matures, ages, and eventually weakens, that decides not just whether lightning will occur at all, but which kind, intracloud, cloud to cloud, negative to ground, or the rarer, more dangerous positive to ground, will happen to strike next. The very first fraction of a second of a lightning strike, before the visible return stroke ever appears, produces a burst of radio noise that spreads out across enormous distances, far further than the flash of light itself can travel, and it was this radio signature, crackling faintly through early radio receivers as an annoying background static, that first alerted radio engineers in the early 20th century to the fact that distant, invisible storms were happening somewhere over the horizon long before any cloud became visible, an early accidental form of lightning detection built entirely from noticing what should have been silence. Modern lightning detection networks, spread across entire continents, now use exactly that same radio signature deliberately, arrays of sensitive receivers spaced hundreds of miles apart that each record the precise instant a burst of radio noise from a distant strike reaches them. And by comparing those tiny differences in arrival time between stations, computers can calculate, almost instantly, the exact location on Earth where that strike occurred, often to within a few hundred meters, turning what was once pure static into a precise, continuously updating map of the sky's activity across an entire nation. A storm's lightning rate often rises and falls in a rough rhythm tied to its own internal life cycle, starting slow as the storm first organizes itself, quickening dramatically as the storm matures and its updraft strengthens, sometimes producing many flashes every minute at its peak, before gradually tapering off again as the storm begins to weaken and rain itself out, meaning that, in a loose but real sense, you can often read the age and strength of a storm simply by listening to how quickly its thunder repeats, fast and urgent in its youth, and slow, scattered and gentle as it finally winds down toward quiet. Certain very tall, very slender natural rock formations and lone desert spires, much like isolated trees and tall buildings, are known among geologists and photographers alike as frequent lightning targets, and some of these formations bear faint, repeated scars from centuries of strikes, subtle fractures and fused mineral deposits that patient researchers can sometimes read almost like tree rings, a long, slow record of exactly how often the sky above that one particular rock has chosen, again and again across hundreds of years, to reach down and touch the same tall, patient stone. Let your own body rest now like one of those old, patient stones, still and unbothered, no longer needing to flinch at any flash or brace for any thunder. Simply here, simply breathing, while the story keeps its own slow, steady rhythm above you, rising a little, falling a little, exactly the way a good storm always does before it finally, gently, passes on. One of the gentler surprises hiding inside the science of lightning is just how little of a storm's total energy, actually goes into the flash we see at all. The overwhelming majority of a thunderstorm's energy is spent simply lifting enormous amounts of water vapor upward, and then releasing it again as rain, hail, and wind. An immense, mostly invisible engine of moving air and falling water, with the electrical spectacle of lightning riding along almost as an afterthought. A small, brilliant side effect of a much larger, quieter process of moisture rising, cooling, and finally letting go. A raindrop falling from a thunderstorm has often traveled a remarkable, looping journey before it ever reaches the ground, carried upward inside the storm's updraft, freezing into ice high in the storm's cold upper reaches, falling partway back down, being caught again by another surge of rising air, and lifted a second or even third time, growing larger and heavier with each pass, gathering more of that same colliding charge that eventually becomes lightning, until it finally grows too heavy for even the strongest updraft to hold, and begins, at last, its final unhindered fall to earth, meaning that the same churning motion responsible for a storm's electricity is also, patiently, quietly, building the very raindrops that will eventually fall as the storm's rain. Hail, in particular, tends to grow largest in the very same violent, churning region of a storm most responsible for generating strong charge separation. And so the largest, most destructive hailstorms and the most intensely electrical storms often turn out, on closer inspection, to be the very same storms, their ferocity in one department closely tied to their ferocity in the other, two loud voices coming from the same single restless throat. Certain very long-lasting flashes of lightning, particularly some rare, sustained cloud-to-ground strokes, can persist not for the usual fraction of a second, but for what researchers have measured, in a handful of remarkable recorded cases, as several seconds at a time, glowing steadily rather than flickering in the usual instantaneous burst. And these unusually long strokes have occasionally been documented stretching for extraordinary horizontal distances across the sky, hundreds of miles from where they began to where they finally touched down, a single continuous thread of light drawn slowly across an entire region's night sky. Meteorologists studying the largest of these extended horizontal flashes have, in recent years, confirmed record-breaking single bolts stretching for distances that would once have seemed impossible, crossing several states in a single unbroken streak. A reminder that even after centuries of study, the sky is still, every so often, capable of surprising the very people who have devoted their careers to understanding it. Let that same sense of unhurried surprise settle over you now too, not the sharp startle of an unexpected flash, but the slow, pleasant surprise of realizing there is always more hidden inside something you thought you already understood, more branching detail folded into every raindrop, every hailstone, every quiet flicker at the top of a distant summer cloud, more than enough, certainly, to keep this story unfolding gently for a very long while yet. Before satellites and radar existed, meteorologists trying to understand the upper atmosphere had to rely on far humbler tools, releasing weather balloons carrying small instrument packages, called radiosondes, up through the very heart of developing storms, measuring temperature, humidity, and pressure as they climbed. And some of the earliest detailed understanding of exactly how unstable, moisture-laden air behaves on its way toward becoming a thunderstorm came from these quiet, unglamorous balloon flights, rising silently into clouds that would, an hour or two later, be flickering with lightning that no one could have fully explained without that same patient data climbing invisibly ahead of it. A bolt of lightning, for all its brightness, is actually a remarkably narrow thing, the visible channel itself often only an inch or two across at its core, though the surrounding glow and the turbulent, heated air around it can appear, to the eye, far wider and far more sprawling than the true electrical channel actually is. A bit like how a single struck match, if photographed carelessly with too long an exposure, can appear to fill an entire dark room with light, when in truth its flame never grew any larger than a fingertip. Some researchers, curious about how frequently lightning has shaped the deep history of the planet rather than just a single afternoon storm, have studied ancient fulgurites preserved in old, undisturbed soil and sand layers, using them much like other geologists use tree rings or ice cores, as a slow, patient record of past atmospheric activity, evidence that this same quiet electrical drama between cloud and ground has been playing out, essentially unchanged. For as long as Earth has had both an atmosphere and a solid surface for that atmosphere to reach down and touch. Certain very specific weather conditions are known among forecasters to be especially favorable for unusually severe or unusually frequent lightning. A layer of warm, humid air near the ground trapped beneath a layer of drier, cooler air just above it, building instability like a lid slowly being pressed down on a pot already beginning to boil, until something, usually a passing disturbance in the upper atmosphere, or simply the accumulated heat of a long afternoon, finally lifts that lid and lets the whole simmering column of air burst upward all at once into a fully formed, lightning-producing storm. Even something as ordinary sounding as a sea breeze, the gentle cooling wind that rolls in off open water on a hot afternoon, plays a quiet, outsized role in triggering storms along many coastlines, because the boundary where that cooler sea air meets the warmer land air acts almost like an invisible wall, forcing warm, humid air upward right along that boundary, which is part of why so many tropical and subtropical coastlines experience such reliable afternoon thunderstorms, arriving with an almost clockwork regularity that longtime coastal residents learn to plan entire afternoons around, without ever needing to check a single forecast. Let your own afternoon, whatever afternoon first taught you to recognize that particular hush before a storm, drift gently back into memory now, not to examine too closely, simply to rest in. The smell of rain still a mile off, the sudden coolness of that first outflow of wind reaching you well ahead of any actual rain, the sky doing, in its own unhurried way, exactly what skis have always done, gathering itself slowly toward release. The same patient gathering this whole story has been describing all along. Mountains, much like tall isolated trees and slender solitary towers, tend to gather storms and lightning around themselves far more readily than flat open plains do, because a mountain slopes force air upward simply by standing in its way, giving that rising air a head start it would not otherwise have on a level plain, which is part of why so many of the world's most reliably stormy regions, from the Congo highlands to certain ranges in the American West, owe at least some of their restless afternoon skis to nothing more complicated than rock standing tall enough to nudge the wind upward. Some of the very earliest written observations of lightning that still survive today come from ancient astronomers and philosophers who kept careful, patient records of the sky for entirely different reasons. Watching for eclipses, tracking the paths of planets, charting the slow procession of stars across the seasons, and yet who could not help also nodding, tucked into the margins of their careful star charts, the occasional dramatic storm that lit up an entire night's observation, an old, quiet habit of watching the sky closely that, in its own roundabout way, laid some of the earliest groundwork for the same careful, patient attention modern meteorologists still bring to every storm today. Lightning's role in early human life was not only mythological but practical too, and there is a long, quiet history of communities in fire-prone landscapes learning to read the pattern of lightning strikes across their own hills and valleys, almost the way one might read a familiar face, learning which ridgelines were struck most often, which valleys seemed to escape the worst of the storms, and passing that hard-earned local knowledge down through generations long before anyone had a scientific vocabulary for updrafts or charge separation. Knowledge built entirely from patient watching, season after season, storm after storm. The exact sound of thunder changes remarkably depending on distance and terrain, a nearby strike producing a sharp, startling crack, almost like a whip snapping directly overhead, while the very same stroke heard from several miles away arrives instead as a long, low, rolling rumble, softened and stretched out by the time its sound has traveled that distance, bounced and scattered along the way by hills, buildings, and the layered, uneven temperature of the air itself, so that the same single event can announce itself as two entirely different sounds, depending only on how far away you happen to be standing when you hear it. Certain animals appear to sense an approaching storm well before humans do, and researchers studying this have proposed a few gentle, overlapping explanations. A sensitivity to the subtle drop in barometric pressure that precedes most storms, an ability to detect the very low-frequency sound, sometimes called infrasound, that a distant storm can produce long before its thunder becomes audible to human ears, or simply a heightened awareness of the changing quality of light and the shifting scent of the air itself, all small quiet clues that a storm's arrival rarely happens without some kind of warning, even if that warning is not always one we notice ourselves. Let your own senses soften now rather than sharpen, the opposite of that alert, storm-sensing awareness, because there is no approaching weather here to prepare for, only this same unhurried voice, still moving steadily through fact after fact, patient as a mountain, patient as an old star charts careful, quiet margin notes. In recent years, the same satellites and detection networks that track ordinary storms have also confirmed several genuinely extraordinary records, single flashes so enormous that meteorologists needed entirely new categories to describe them. One single flash recorded over the southern United States was measured stretching for well over 400 miles from one end to the other, a single continuous thread of electricity longer than many countries are wide, and a separate flash recorded over South America was found to have lasted for more than 17 seconds from its first branch to its final fade, both records standing as quiet, almost unbelievable proof that even after centuries of careful study, the upper limits of what a storm can produce are still being discovered, patiently, one extraordinary satellite pass at a time. A small number of people across recorded history have been struck by lightning not once but many times over the course of a single life, and the most famous of these is often cited as a park ranger in the United States, who was reportedly struck on 7 separate occasions across several decades of outdoor work, surviving every single one, though each strike left him with real injuries and a long, difficult recovery, a life that became, almost against his own wishes, one of the most studied individual case histories in the entire field of lightning safety research, offering researchers rare, repeated first-hand insight into exactly how a human body responds to being struck. Lightning's interaction with radio waves extends well beyond the simple detection networks already described, and long-distance radio communication in the era before satellites often depended on bouncing signals off the upper atmosphere, a layer that distant thunderstorms could disturb or distort in ways that puzzled early radio operators long before anyone connected the strange static and fatting signals to storms happening thousands of miles away. A quiet reminder that the atmosphere's electrical life does not stay neatly confined to the sky directly overhead, but ripples outward in its own invisible way across enormous distances. Some of the most striking early photographs of lightning, taken in the final decades of the 19th century, once camera exposure times had grown fast enough to have any hope of capturing something as brief as a flash, revealed for the first time the true jagged, branching complexity of a bolt structure, overturning centuries of artistic tradition that had always drawn lightning as a smooth, simple zigzag. And it is a small, gentle reminder that even something as constantly visible and universally recognized as lightning had to wait for the right technology before humanity could finally see its true, intricate shape clearly. Certain lightning strikes, rather than traveling cleanly through open air from cloud to ground, instead find and follow existing paths of least resistance once they reach the surface, arcing along damp soil, following buried pipes or wiring for some distance, or leaping between two closely spaced trees or fence posts in a phenomenon sometimes called a side flash, meaning that a person or animal standing near, but not directly beneath. A struck object can still occasionally be reached by a strike that never intended to travel that far at all. Another small, quiet piece of the reasoning behind old advice: to keep a generous distance from isolated trees during a storm. Let all of that jagged complexity, all those branching side paths and buried currents, blur now into something softer, something more like the branching veins of a leaf held up to a gentle light, intricate but calm, complicated but never frightening. Because tonight none of it is reaching for you at all, only drifting past, fact by fact, on its own unhurried way toward wherever this long story is eventually headed. The very air a storm moves through changes its behavior in ways that meteorologists have only slowly learned to measure precisely. And one of the more delicate variables is humidity itself, because a thunderstorm forming over unusually dry ground, even with plenty of instability in the air above it, often produces those dry lightning strikes described earlier, dangerous precisely because so little rain accompanies the flash. While the same storm forming over well-soaked ground tends to bring heavier rain right alongside its lightning, giving each strike a better chance of landing somewhere already too wet to easily catch fire, a small, quiet mercy built into the very ground beneath the storm. The concept of grounding, so central to lightning safety and lightning rods alike, is really just the simple idea of giving electrical charge the easiest, most direct path toward the vast, electrically neutral body of the Earth itself, which is large enough and conductive enough to absorb an almost unimaginable amount of charge without any noticeable change to itself at all, meaning that in the end, every single lightning strike that ever reaches the ground is simply charge returning home, seeking. However dramatically, nothing more than the same quiet equilibrium water seeks when it finally settles level in a still pond. Engineers designing modern skyscrapers now often incorporate lightning protection directly into the building's structural steel itself, rather than relying on a single rod at the very top, treating the entire frame as one enormous, continuously grounded conductor, capable of accepting a strike almost anywhere along its height, and channeling it safely downward. A quiet evolution of Franklin's original simple spike into something far more thoroughly woven into the very bones of a modern building. Some of the most visually striking lightning photographs ever captured show multiple strokes occurring within the very same channel in rapid succession, because a single flash of lightning is very often not really a single event at all, but rather a rapid series of several return strokes traveling down almost the exact same ionized path within a fraction of a second of each other, which is part of why some lightning appears to flicker or strobe rather than simply flash once. Each individual stroke usually invisible to the naked eye as a separate event, blurring together into what looks, to us, like one single continuous flash of light. The study of lightning has, over the past century, slowly grown into its own quiet, specialized corner of atmospheric science, complete with dedicated research aircraft flown deliberately close to active storms, specialized high-speed cameras capable of recording tens of thousands of frames every second, and international collaborations sharing satellite lightning data across borders in real time, an entire patient global effort built around understanding, in ever finer detail, something that has been flickering across our skis for as long as our planet has had both an atmosphere and weather within it. Let this description of careful cameras and patient international collaboration settle now into something far simpler, just the quiet reassurance that somewhere right now, instruments far more attentive than any tired human eye are already watching every storm on Earth, so that you, resting here, do not have to watch anything at all. Only listen, only breathe. Only let this voice keep gathering its slow facts the way a storm gathers its own quiet, patient charge. A thunderstorm's downdraft, that cold rush of falling air already mentioned, often reaches the ground well ahead of the rain itself, spreading outward in a sudden gust called the gust front. And this is very often the first physical sign of an approaching storm that people actually feel on their own skin. A sharp, cooling wind arriving out of nowhere on an otherwise still, warm afternoon, kicking up dust and loose leaves and sending window curtains fluttering inward. A small, cool herald sent ahead of the main event, giving anyone paying attention a few final quiet minutes to find shelter before the first flash ever appears. Certain long-lived storm systems, particularly the especially organized and especially dangerous kind called supercells, maintain a single, rotating updraft for hours at a time rather than the shorter, simpler up-and-down cycle of an ordinary storm. And this sustained rotation allows a supercell to keep separating and building charge far longer and far more intensely than an ordinary storm ever could. Which is part of why supercells are responsible for a disproportionate share of the most extreme lightning, largest hail, and most severe winds recorded anywhere on the planet. A single storm behaving almost like a small, self-sustaining weather system all its own. Even the pattern in which lightning flickers within a single storm can hint at what that storm is about to do next, and some researchers studying severe weather have found that a sudden, dramatic spike in a storm's overall lightning rate, sometimes called a lightning jump, often precedes the onset of severe conditions at the ground by 10 or 15 minutes or more, meaning that in some cases, the storm's electrical chatter is quietly announcing trouble to come before radar, or any human observer on the ground, has any other clear sign that anything unusual is happening at all. The word thunder and the word lightning both carry old, tangled roots stretching back through centuries of language, evolving through Old English and further, still into shared ancient Germanic and Indo-European roots describing sound and sudden brightness. A small linguistic echo of just how long people speaking the ancestors of English have needed words at all for this particular pairing of sight and sound. The flash and the answering roar arriving together in nearly every language humans have ever spoken, each one finding its own way to name the same old partnership. Across the many mythologies already described, from Zeus to Thor to Shango to Indra to the Thunderbird, there runs a quiet, shared thread worth resting on for a moment, that nearly every civilization independently decided lightning was too vast, too sudden, and too final to belong to ordinary mortals at all, and had to be lifted instead into the hands of something greater, a small, humble reminder that awe, real unforced awe at the natural world, is one of the oldest and most universal feelings our species has ever shared, long before any of us had the physics to explain exactly what we were so awed by. Let that shared, ancient awe settle over you now, not as something urgent, but as something almost like a lullaby in itself. The knowledge that everyone who ever lay listening to a storm before you, in every age and every place, felt some version of this same small wonder, and simply let that wide, gentle company be enough to carry you further down into rest. A lightning strike's true electrical current, at its absolute peak, can reach values measured in the tens of thousands of amperes, a number so far beyond anything found in ordinary household wiring that it becomes almost meaningless as a comparison, more useful simply as a measure of just how much charge a mature storm has managed to gather before finally releasing it all at once, a number large enough to instantly vaporize a narrow channel of air into glowing plasma, and yet released so briefly, so fleetingly, that the total energy delivered remains, as this story mentioned earlier, still fairly modest compared to the storm's much larger, quieter expenditure of energy on lifting water through the sky. One of the more delicate ongoing debates among atmospheric scientists concerns exactly how a storm manages to separate so much positive and negative charge so quickly in the first place. And while the basic picture involving colliding ice and graupel, already described, captures the dominant explanation, researchers continue to study finer details. The exact role of temperature at the moment of collision, the precise size and shape of the colliding particles, and how liquid water coating those particles might change the outcome. A reminder that even the most basic seeming step in this whole slow story, simple ice bumping into other simple ice, still holds small, unanswered corners that patient scientists are still, quietly, working through. Lightning safety recommendations extend into some surprisingly specific everyday situations that might not occur to someone simply picturing an open field. Advice to avoid taking a shower or bath during a severe thunderstorm, since metal plumbing can, in rare cases, conduct a charge from a strike on the building into the water system. Advice to avoid using corded telephones during a storm for similar reasons, though cordless and mobile phones carry no such risk. And advice to stay away from windows, not primarily because glass conducts electricity, which it generally does not, but because a nearby strike can sometimes send debris or a side flash toward an open or poorly sealed window. Certain wildlife researchers studying particularly lightning-dense regions like the Catatumbo area have noted, with quiet interest, that some local ecosystems appear to have adapted subtly around the near-constant nighttime flicker. Insects and nocturnal animals whose behavior seems tuned, in small ways still being studied, to that unusually frequent, rhythmic light. A reminder that even something as dramatic as nightly lightning can, given enough time, simply become another steady feature of a landscape's ordinary rhythm, rather than remaining forever remarkable to the creatures who actually live beneath it. The idea that lightning never strikes the same place twice is one of the oldest, most confidently repeated pieces of folk wisdom about storms, and it is also, quite plainly, false. Tall structures, isolated peaks and prominent landmarks are struck again and again, sometimes many times within a single storm, precisely because whatever made a place a likely target the first time, its height, its isolation, its conductivity, generally has not changed by the time the next storm rolls through. And so the sky, in its own patient way, simply keeps returning to the same easiest paths, storm after storm, year after year. Let that gentle correction settle over you softly rather than sharply, not as a fact to argue about, simply one more small thread in the same slow, unspooling story. One more reminder that the sky, for all its drama, tends to behave according to patient, repeatable, almost boring physical rules. The same rules quietly followed tonight, as they were followed the very first night a storm ever gathered over this old, patient planet. Some of the oldest surviving fulgurites ever studied by scientists have been dated to many thousands of years old, preserved quietly underground in stable, undisturbed sand long after the storm that created them had passed and been forgotten by everyone who might once have watched it, meaning that somewhere beneath certain quiet dunes and old riverbanks right now, there are likely still slender glass fingers pointing down toward strikes that happened long before any written history existed. Small silent monuments to storms no one alive remembers, waiting patiently, the way fossils always wait, for someone curious enough to dig. The overall global rate of lightning is not perfectly constant year after year, but shifts gently with larger climate patterns. And researchers studying long-term satellite records have found that certain broad shifts in ocean temperature and atmospheric circulation, the kind that also influence rainfall and drought across entire continents, can nudge the total amount of lightning activity slightly up or slightly down from one year to the next. A reminder that even something as immediate and local as a single flash overhead is quietly connected, thread by thread, to much larger, slower patterns moving across the whole restless system of the planet's air and ocean together. Certain very specific building materials and architectural choices can meaningfully change how well a structure survives a direct strike, and older buildings constructed with tall wooden or brick chimneys, lacking any dedicated grounding system, have historically proven more vulnerable to real damage than modern buildings designed from the start with lightning protection in mind, which is part of why lightning protection standards, quiet and unglamorous as they are, have become such a standard, almost invisible part of modern construction codes in many countries, A small inherited gift from Franklin's original curious spike, still working, still largely unnoticed, above millions of rooftops tonight. Even something as specific as the shape of a cloud can offer an experienced storm watcher a rough, informal sense of how much lightning to expect. A tall, sharply defined tower with a hard, bubbling edge climbing rapidly upward generally suggests a strong, vigorous updraft still building, often a reliable sign of active or imminent lightning, while a softer, more diffuse, slower-moving cloud mass, lacking that same sharp vertical energy, tends to produce less frequent and less intense electrical activity, a small, visual shorthand that generations of farmers, sailors, and shepherds learned to read long before anyone offered them a scientific explanation for why it worked. Lightning research has, in recent decades, also turned its attention toward its own quiet cousin, a phenomenon called upward positive leaders, sometimes seen reaching from tall wind turbines during storms. And as wind energy has expanded rapidly around the world, engineers have had to study, in careful new detail, exactly how these especially tall, especially exposed, constantly rotating structures interact with the electric fields of passing storms. Adapting blade materials and internal grounding systems to handle strikes that older, shorter structures rarely needed to plan for at all. A modern chapter in this very old story of tall things and reaching charge, still quietly being written. Let all of that quiet modern engineering fade now into something softer still, not blueprints or grounding diagrams, simply the image of a distant turbine or a distant chimney or a distant old dune standing patiently beneath a moving sky, none of it needing your attention any longer, all of it simply continuing to exist, calmly, the way this story intends to keep continuing gently for as long as it takes. A storm's lightning does not distribute itself evenly across the whole life of the storm, but tends to cluster heavily around the storm's most mature, most vigorous phase, meaning that the middle portion of a storm's passage overhead is very often, statistically, the most electrically active window of the entire event. A pattern careful long-term observation has confirmed again and again, storm after storm, season after season, until it became one of the quiet, reliable rules meteorologists now teach to anyone learning to read a storm's whole arc from first distant rumble to final scattered drop. Certain very rare storms manage to produce what researchers sometimes call a positive giant flash, an unusually powerful positive cloud-to-ground stroke originating from the storm's uppermost, most far-reaching charge region, and these rare giant flashes are believed to be responsible for a disproportionate number of the most severe wildfire ignitions on record. Since their higher energy and longer duration give them a better chance of actually igniting dry fuel on the ground compared to an ordinary, quicker negative stroke. One more quiet reminder that within the broad, general category we simply call lightning, a wide range of very different individual events are actually taking place. The study of lightning's role in wildfire ignition has grown into its own careful subfield within fire ecology, with researchers mapping, region by region, exactly which combination of dry fuel, terrain, and storm type tends to produce the most lightning-caused fires, work that has become increasingly important as forest managers try to distinguish between fires that might be allowed to burn as a natural, healthy part of an ecosystem cycle, and fires that pose a genuine risk requiring rapid suppression, a careful, patient balancing act built on understanding lightning not simply as a hazard, but as one of the oldest tools shaping forests long before any human ever tried to manage one. Even something as seemingly small as the moisture content of the soil directly beneath a storm can influence how a strike behaves once it reaches the ground. Wetter soil generally conducting a strike's current away more quickly and more widely than dry, compacted ground, which tends to concentrate that same current more narrowly and can, in some cases, produce more localized damage right at the strike point. One more small variable in the long list of quiet factors that decide exactly how any single flash's story ends once it finally reaches the Earth. Across the long history of human settlement, certain especially prominent buildings, cathedral spires, ancient watchtowers, and old wooden church steeples among them, were struck by lightning so often before the invention of the lightning rod that some communities developed their own local folk explanations entirely separate from any national mythology, blaming a particular bell, a particular weather vane, or a particular unlucky year. Small local stories layered on top of the same simple physical truth already described many times in this documentary, that height and isolation, far more than any curse or blessing, decide where a storm's leader is most likely to finally find its answering spark. Let all of those old local stories, cathedral bells and unlucky years and half-remembered village explanations, settle now like sediment at the bottom of a still, slow-moving river, none of them needing to be sorted or corrected tonight, simply resting there together, old and new science layered gently over even older folklore, while this voice keeps moving on, patient and unhurried, toward whatever quiet fact comes next.